In our previous video, we found the confidence interval for a mean where the standard deviation in the population, so the variability in the data, was known for the population. But what if we don't know the standard deviation or variability in the population? In fact, it's more likely than not that we don't. If we don't know the population parameter, the mean, why would we know the variability in the population as well? So in most sampling situations, the population standard deviation sigma is not known. We can use the sample standard deviation to estimate the population standard deviation. So we can use S as a point estimate for the population standard deviation sigma. When we substitute S for sigma, though, we can no longer use the standard normal distribution. So what we're actually going to be using is what is called a t-distribution. Student's t is its exact name. So around 1908, the student's t-distribution was created by a man named William Seeley Gossett. Gossett worked for the Guinness Brewery Company in Dublin, and his job was to make sure that the beer had a consistent taste. So every bottle of Guinness tasted the same. However, Gossett had small samples, so the central limit theorem really couldn't come into play. Another researcher at Guinness had previously published a paper containing trade secrets of the Guinness Brewery. To prevent further disclosure of confidential information, Guinness prohibited its employees from publishing any papers regardless of the information it contains. So they're quite concerned that even though they are statistical research methodology papers, that it was revealing too much about their proprietary information, their trade secrets. So this meant that Gossett was unable to publish his work under his own name. Therefore, he used the pseudonym Student T to avoid detection by his employers in his publications. And so that's why you get the student's T distribution as opposed to Gossett's distribution. So what is the student's T distribution? The student's T distribution is a continuous distribution. So we have a probability density function. And it is bell-shaped and symmetrical, similar to the normal distribution. It is asymptotic. Do you remember what the term asymptotic means? We talked about it previously. So when we talk about asymptotic, we're talking about these tails here get closer and closer to the axes but never touch. And my drawings are always terrible because mine show them go back up. They don't go back up. They get closer and closer and closer but never touch. What does that mean? That means that those extreme values, the probability of those extreme values, whether they're extremely high or extremely low, the probability is teeny tiny. It's not zero, it's not impossible, but it's teeny tiny. And the more and more extreme, the more teeny tiny it is. So the T distribution is actually a family of distributions because different sample sizes have different distribution shapes. So when we look at a T distribution here, you can see that they all look very similar. They're all bell-shaped, they're all continuous, they're all symmetrical, they're all asymptotic. But how big the tails are, how tall the distribution is, how narrow or wide it is going to vary depending on the sample size. All T distributions have a center around 0, so it's going to be similar to that standard normal distribution. But the smaller the sample sizes, the larger the variability, so the standard deviation is going to be bigger and it's going to be flatter. Okay. The larger the sample size, the more it gets to be a normal distribution. So what's the difference of finding a confidence interval for means with a T distribution than a standard normal distribution? Well, still the center is T equals 0 or 0. The difference here instead of Z's is T's. So we have a minus T and a plus T for our distribution, which means we can't use the standard normal table. It means that we have a different distribution. And we need to find a t-score. Well, t-score is x bar minus mu s divided by the square root of n. So just like the standard normal, but here we have S for the standard deviation of the sample instead of the population. So if we're doing confidence intervals for means using the t distribution, we are assuming random sampling. Again, we need the data in our sample to be similar to the population so we can extrapolate. We are assuming that the population is normal or that the population is not normal and the sample size is big enough. So we're still trying to apply that central limit theorem. The only difference here is we don't know sigma. And if we don't know sigma, we are then adjusting that normal distribution with the sample standard deviation. So we're going to use a t-score instead of a z-score with an s instead of a sigma. Okay. So we're going to need a t-table to use our t-statistic. So if we're looking at a t-distribution table, here's one from the University of Miami. And you can Google, there's lots of t-distribution tables. We'll show you how it looks. In this particular t-distribution table, let's just make it bigger here. What it tells us, so always if you're using a table, check to see how it's giving you the information. In this particular instance, what it's doing is it's looking for the area to the right. And so when we look at a t, here's a t 0.05, that means this area here is 0.05. Now, when we use a t-distribution, it's just like when we did the z-scores, we are looking for a confidence interval which is in the middle. So if you're using a table like this and it's giving you the far right, we need to identify the fact that if we have a 95% confidence interval, our alpha is 0.05, but the tail here, we're splitting the two tails on the two sides, this is going to be 0.025. So that means that this column here will give you 95%, where it's 0.025. If we're doing 99%, then that's an alpha of 0.1, and then that is 0.05. So this is your 99%. And if you are doing a 90%, then that's an alpha of 0.1. And I got these mixed up here. Let's do this. Let's write it out. 99%. 99% has an alpha equal 1%. Alpha divided by 2 is not 0.01, but 0.01 divided by 2, which is the 0.05. So this should be your 99%. And if we are doing a 90%, then our alpha equals 10%. So that's 0.1 divided by 2, which is our 0.05. So this should be our 90%, 95%, 99%. Well, what we said just a moment ago is that, I don't know where I put it, somewhere, that the big sample sizes for a student t distribution give you a normal distribution. And so if you're using a t distribution table and you're never quite sure, go down to the bottom of your t distribution table and you should see those same z-scores that you use with 90, 95, and 98. So 1.645, we were using 1.6, but remember it was kind of right in between. 1.96, and then 2.58 is what we were using. Exact here is 2.576. So that way we can make sure that we're at the right spot. So 90%, 95%, 99%. Well, once you have your t distribution table, then the process is going to be just like it was with when we knew the standard deviation of the population. So if we go here, we have our t-score, our t-statistic, and our confidence interval is going to be dealt with the same way. We found our t's. Now, the only thing is when you use a t-table or you're finding your t-scores, not only do they depend on what alpha is, the level of confidence you're going to have, how much error you're willing to have, but they also depend on sample size. Okay, so if I wanted to do a 90% confidence interval with a sample size of 31, then I need to look up on the table our degrees of freedom of 31 minus 1. So notice this n minus 1 here. And that's because we're using the sample standard deviation, which is going to depend on the sample average. Because of the relationship between those two statistics, we actually lose what we call 1 degree of freedom. There's a relationship between the numbers that we're trying to estimate, or we're using to estimate. So if you're to do this, we're doing degrees of freedom of 31 minus 1 and a 90% confidence interval. So we would go to degrees of freedom, 31 minus 1 gives us our 30. And if we're doing a, 95% confidence interval? No, 90% confidence interval, we would use a t of 1.697. Plus or minus, because we're going to do our formula just like we did before, where we have our point estimate plus or minus, and then this time we'll have our t, which depends on alpha and degrees of freedom, and then we'll have s divided by the square root of n. So just like before, we'll have the point estimate plus the margin of error. We need to find out what that t is. What if we have a sample size of 10 and we want a 95% confidence interval? Then we go here, we had, oh, my brain's not working today, sample size of 10, which means our degrees of freedom are 9. And we want to have a 95% confidence, so we go here, 95%, and we'll use a t of 2.262. Okay. If we have a sample size of 56 and we want a 95% confidence interval, degrees of freedom, 56 minus 1 is 55, and we want 99% confidence, so 55. Now, notice there's no 55. The bigger we get, and a lot of these t-distribution charts, what they do is after 30, they just go to the z-scores. This one goes to kind of 38 and then goes that way, so a little bit more precise in that interim. But the t-distribution becomes that standard normal distribution the larger the sample size. And so in this case, because we don't actually have 55, we're up above the 30 here, we really are just using the standard normal. So we would do 99% and we'd be at 2.58. Or if you want to be precise, 2.576. Okay, so this number here matches what we would do if we knew the standard deviation for the population because the sample size is sufficiently large. Okay, what do we do with all this? Well, once we have t, then we can plug into this to find the upper and lower bounds for our confidence interval. We have our point estimate, that's our sample mean, and then we take our t-score and we multiply it times the sample standard deviation divided by the square root of n. So this image here is just showing you how we end up there. If we start out with the lower bound being on our negative t and our positive t for our 95%. What's in the middle there is your t-score, x bar minus mu divided by s over the square root of n. We could then multiply s divided by the square root of n to both sides. We then take x, and that's how we end up with this point estimate plus or minus t alpha divided by t n minus 1 times s over the square root of n. We're just rearranging this math formula so that we end up with mu being what we're trying to approximate. Okay, so x bar plus or minus t, which depends on alpha divided by 2 and n minus 1, s in the square root of n. Okay, so differences. The only difference here, z, t, depending on whether or not you know the variability in the underlying population. So let's suppose that we're back to our battery example and we're investigating the length of time a battery will last between charges at a fixed load. A sample of 12 batteries had an average length of time of 4.3 hours, a standard deviation of 0.25. We don't know the standard deviation of the population. We simply have the standard deviation of the sample. So for a 95% confidence interval, what do we use for t? Well, n is equal to 12. So our degrees of freedom is 12 minus 1, 11. And our confidence level is 95%. So what do we use here? Degrees of freedom, 11. We want 95%. Remember, 95%, that means that there's 5% error. Half of that goes to the right, half of that goes to the left. So we're going to use 2.201. So our t is 2.201. We have a positive 1 and a negative 1. So let's construct our confidence interval. Our confidence interval, remember, is x bar plus or minus rt times s over the square root of n. So here we have a mean length of 4.3 plus or minus our t of 2.201. And then we have our sample standard deviation of 0.25 divided by the square root of 12. All right, let's pull up our Excel and do this calculation. We'll do the margin of error first. So we'll start with our square root of 12. Of course, got to use the right formula. We need an SQRT for 12. And we're going to do equals 0.25 divided by that square root of 12. Okay. And then we're going to multiply that times our t, which was 2.201. So we have a margin of error here of 0.1588. And then our lower bound is going to be that 4.3 minus equals 4.3 minus our, stop doing that. 4.3 minus our margin of error. And then our upper bound is going to be 4.3 plus our margin of error. So here we have that the battery, for all the manufactured batteries, the average life is going to be between 4.14 hours and 4.45 hours. So just to give you a comparison, here's what it was with the normal distribution, 4.13 and 4.4697. So you can see in this case that it's a bit of a narrower confidence interval here with that sample standard deviation. So is it reasonable to claim that the battery will last 4.25 hours? Yes, because it's between the upper and lower bound. Is it reasonable to claim the batteries will last 5 hours? No, that's too extreme for what we can be 95% confident about. Now, when we did this previously with the normal distribution, we used equals confidence.norm to do this calculation without the t distribution or the standard normal table. So if you don't have a table, you want to do this entirely in Excel. If you know the standard deviation of the population, we used equal confidence.norm. Here, we're not doing equal confidence.norm. We're doing equal confidence.t. So that it will use the t distribution instead of the normal distribution. So it's going to ask for alpha, standard deviation, and size. It knows by being a t that it is going to be the sample standard deviation instead of the population standard deviation. So alpha here is 0.05 because we're doing a 95% confidence interval. So what's remaining is the 5% error. And the standard deviation here is the standard deviation for the sample, which was 0.25. And then our sample size was 12. And what did I do wrong? Missing a comma. All right, 0.05, 0.25, comma, 12. Okay. All right, so remember, this is just the margin of error. So these numbers should match here. If you want to actually get the lower and upper bound, what we have to do is take our point estimate of 4.3 and subtract that margin of error. Of course, it's got to be equals, not negative here. Equals 4.3 minus the margin of error gives the lower bound, equals 4.3 plus the margin of error gives us the upper bound. 4.14 to 4.46 is the range that we can be 95% confident of. And here the difference is we don't have the standard deviation of the population, only of the sample.